I'll share my screen with you. Is it visible to you?
Yes, ma'am.
Okay, so we are going to study compiler design. So first we'll start with compiler. So what is basically compiler and what is its responsibility? So we, the programmers, we generally write a program in high level language. Okay, because why do we prefer to write in high level language? Because that is what we are comfortable with. We are comfortable with English. Okay, we are not comfortable with binary or any intermediate kind of language. Though long ago, people used to write the programs in assembly language also. But then it was found that we are more comfortable with English. We understand what is print, what is scan, okay, what to include and all. So we thought that, okay, let us write it in English and then we can convert it to machine language later. So that is when we started the writing the programs in high level language. Okay. High level language. So that is the reason we don't write directly into the program in machine language. Okay. And hence comes the role of compiler, because the compiler need to convert it now. So what happens? What are the various phases of compiler? So here you can see the various phases. Okay. So first is the preprocessor. So what happens? The preprocessor converts the high level language to pure high level language. Okay. High level language to pure high level language. Now what is pure high level language? So you see in our programs, we have some statements like hash include, hash define. Okay. Other than that, what do we have? We have comments. So all these things need to be removed. Okay. So whenever we eliminate hash include, there is a header file here, right? Name of a header file. That is asked to be included. So this is basically called file inclusion. Okay, file inclusion. Another is hash define. What is hash define? Anyone? What is hash define? What is this called? Hash define. This is macro, right? We call it macro expansion. Like hash define pi 3.14 if I write down. Because pi is a constant value that does not change. That means what? We are defining the value of pi to be 3.14. So whenever we use pi in the language, in the program, then its value will automatically be considered as 3.14. And we cannot, change that value. This will not be treated like a normal variable. Okay, its value is defined, that is 3.14. Similarly, in cases like interest, okay, so in bank, for certain programs, the interest is fixed. In that case, what happens if we fix the interest here as hash defined, then we don't have to change the interest everywhere. Even if the interest is changed after a few years, you can change it in the hash defined portion. Okay, so these type of things are there, which is the responsibility of preprocessor. So when all these things are done, the file is included, and in case of macro, that is hash defined, whenever in the program we have pi, that value will be replaced by 3.14. Okay. And after doing all these changes and removing the comments, whatever we get, whatever the result we get, that is called a pure high level language. Okay, so that is called a pure high level language. And then this pure high level language is given as input to the compiler. Okay, so compiler basically takes this pure high level language as input and converts it to assembly language. Converts it to assembly language. Okay, so what is assembly language? Assembly language is neither, high level language nor actually machine code. It is somewhere in between, intermediate. Okay, not totally high level and not totally machine code. So that is a assembly language. So if I talk about only compiler, okay, then it converts a pure high level language to assembly language. But in the compilers that are available like GCC or Turbo C, okay, in that case, all these steps are part of the compiler. All these steps are included in the compiler. That is why, you directly get the machine code and you run the program. So now this assembly language will be given as input to the assembler. Okay. Now what is assembler? Assembler is actually machine dependent. Like for a particular machine, you get a, book with it, that is manual, how to run that particular machine. Okay, so the manual of one machine will not work for the manual of another kind of machine. Same way, assembler is also machine dependent. Okay, so the assembler of one kind of, hardware will not work for another type. So the assembler will take the assembly language as input and it will give the output, that is the machine code. Okay, the output is machine code. Now machine codes are of two types. Okay, machine codes are of two types. One is relocatable. Another is absolute. What are these actually? We'll come to it later on. As of now, you know that the assembly language is given to the assembler as input and the assembler will give the machine code, the relocatable machine code, as the output. Okay, relocatable means you can move this code, okay, in the hardware because you have to store the variables. Okay, so you can relocate it. But after this relocatable machine code is given as input to the loader or linker. Okay, to the loader or linker, which will give you the executable code, which is the absolute machine code. Okay, so what is this will come when we will study each step in detail. We'll come to this. Okay, as of now, you just know that these are the phases of a compiler. So what are the phases we learned? High level language is given to preprocessor, which converts it to pure high level language. Okay, this pure high level language is given to the compiler as input, and in the output we will get assembly language. This assembly language is given as input to the assembler. Okay, so this assembler is like I said it's like a manual. Okay, it's like a manual to the machine. You just understand as of now, you don't have to take any notes or write down anything. I will share this PDF with you. Okay, so don't have to bother about it. Just try to understand whatever I'm saying. So the assembly language is given as input to the assembler and the assembler gives the output, that is the machine code, in the relocatable form. Okay, so relocatable machine code is the output of the assembler and this is given to loader or linker, and with the help of loader and linker, the output, final output we get is the executable code that can be executed, final code. Okay, and it is absolute machine code. Up to this clear, everyone? Please let me know if it is clear to you.
Yes, ma'am, it is clear.
Okay. So steps are, I have discussed all the steps here. Okay. You can go through it as theory. I'll share it with you. It's not a problem. Now, this is the important part, which is called phases of a compiler. So there are two phases, analysis phase and synthesis phase. Okay, these are the two phases of compiler. One is called analysis phase, another is called synthesis phase. So what happens, the high level language, that is the pure high level language I'm talking about, that will go to the lexical analyzer. Okay, this one I'm talking about the compiler only, not anything else, only the compiler. And what is the input to the compiler? The pure high level language. Okay. So in the compiler, what happens? The first stage is called lexical analysis stage. Okay. So the first stage is called lexical analysis. I'll explain these steps one by one. Don't have to worry. So for this, we have a lexical analyzer. Okay. And what is the responsibility of the lexical analyzer? The lexical analyzer will analyze the lexemes. Okay. These are the meaningful statements, lexemes, and it will convert those into stream of tokens. Okay. It will convert those into stream of tokens. So what are the stream of tokens? What is lexemes? How it is converted? We'll see everything with the help of an example. Then it will be clear to you. Just as of now, just go through the steps. So now this, with the help of this stream of tokens, the next step that we will go to in the compiler is the syntax analysis stage. For that, we have syntax analyzer. Okay. And what the syntax analyzer will do? The syntax analyzer will create the parse tree. Okay, will create a parse tree. Is a kind of a tree which is created with the help of certain grammars. Okay, certain predefined grammars, which is for every language there are some context-free grammars already present. Using those grammars, the parse tree is created for the input, and if it matches with the kind of input that we have, then we will say that there is no syntax error. Okay, so for detecting the syntax error, we have this phase which is called the syntax analysis phase. And this is done using a syntax analyzer. Okay. And once this is done, once a parse tree is created and it is checked, if there is no syntax error, then it will move on to the next phase, which is called semantic analysis phase. Okay. Semantic analysis phase. Here what will happen, there is a semantic analyzer. What it will do, it will check the parse tree. Okay, it will verify it semantically. As we know that syntax error and semantic error are not same. Okay, there is a way of writing a sentence or a line in a program. If that is incorrect, that is your syntax error. Okay. If there is any logical error, that actually comes under semantic error. Okay, so this parse tree will be verified semantically by the semantic analyzer. So what is the output? The output is still a parse tree, but it is semantically verified parse tree. Okay, so here input is a parse tree and output is also a parse tree, but what is the difference? The output parse tree is semantically verified. Okay, so from here, the next step is the intermediate code generator. Okay, so this will create intermediate code. Now we will learn that there are various types of intermediate code, but the most popular one used is the 3 address code. So what is the output? The output can be different types of intermediate code, but the most popular one is the 3 address code. Why it is 3 address code? When I will tell you the example, you will easily understand it. Okay. And this 3 address code will next go to a phase called code optimizer. Now, what is optimization? Optimization means reduction. Okay. So whatever steps are there. Okay. Suppose 3 address code, we get 5 lines. So what this code optimizer will do, it will try to reduce it to 2 lines or 3 lines. Okay. That means keeping the meaning same, meaning should not be altered. Keeping the meaning same, if any optimization is possible, then that will be done in the code optimization phase. Okay. And after that, we have target code generation. Okay. So finally, we will generate the target code and we will get from there, we'll get the assembly code. Now, did you study microprocessor? Did you have the subject called microprocessor? Anyone? Or anything of machine code you have learned in analog or digital, anything, anywhere? In computer organization, have you learned? Like this type of instructions, move, R1, R2, where there are registers.
Yes, ma'am. I have learned in microprocessors.
Okay, Animesh, I think you are lateral, so you know that. Others, you have any idea?
Yes, ma'am, I have.
Yes, ma'am. It was there in computer organization.
Okay, then it is easy for me to explain. Okay, so now we will explain the steps one by one so that it becomes easy for you to understand. And because this is the last step, is not in assembly language, we'll get this type of things. So I just wanted to know whether you have idea. Okay, now all these things will take help from something. All these steps or all these stages will need the help of something called symbol table. Okay, it's a data structure. What is symbol table? It's actually a data structure which stores some information, and the information keeps modifying in the subsequent stages. Okay. And another is error handler. This is a module which they will have to interact with in all the stages. So this is all about the phases of a compiler only. Okay. I'm not talking about preprocessor or other things, just purely compiler. So now we will understand lexical analysis to target code generation one by one using a simple example. So first is lexical analyzer. Okay. So it will take the pure high level language program, read it and convert it into stream of tokens. So let us see an example. So let us consider this is a line. This is a code. Okay, this is a piece of code. So for keeping it simple, we have assumed a one-line source program. It is a one-line source program. What is it? X is equal to A plus B into C. Okay. So what it will do, what it says basically, multiply B and C, then add A and store the result in X. Why multiply B and C first? Because that is what we have learned. Okay. This has higher priority. Multiplication has higher priority than addition. So B into C will be first done. Then addition with A, and the entire result is to be stored in X. That is the meaning of this particular line. So what will happen in lexical analysis stage? So this will be given to the lexical analyzer. Okay. So once the lexical analyzer receives the input, it is converted into stream of tokens like this. Okay. into stream of tokens. What is it? It is identifier is equal to identifier plus identifier into identifier. So what is this identifier basically? Suppose identifier, which one you will be calling an identifier that will be predefined, that will be given to the compiler. Okay. Suppose it is given to the compiler where L stands for letter and D stands for digit. Now, can you tell me what is the meaning of this if you have learned TOC? This is what an identifier is. Suppose this is specified, this is given to the compiler, that if you get something like this, then you call it an identifier, where L is letter and D is digit. Now, this type of expressions, I hope you have studied in TOC. Now, can you tell me what it is? How to read it? You have seen this type of expressions, right?
Yes, ma'am.
Can you tell me the meaning of this? What is the lowest value of this star?
1
1 or 0?
star maybe.
This says that if you get a letter followed by any number of letter or digit, then you call it an identifier. Okay? So even if it is a single letter and this value is 0, then also it is identifier. If this value is 0, this will become 1 and there will be a single letter, right? So if you have a single letter or a letter followed by any number of letter or digit, then you call it an identifier. That is what is given to the compiler. That instruction is given to the compiler. That is how the compiler is identifying that X is an identifier, right? And the compiler also knows that equal to, plus, multiply, all these are operators. So we will not change the operators. We'll keep the operators as it is. And then A is a letter, so it is an identifier. B is a letter, so it is an identifier. And C is also a letter, so it is an identifier. So what do we finally get from this one? We get ID is equal to ID plus ID into ID, where ID is identifier and plus multiplication equal to, all these are operators. So this is one of the jobs of lexical analyzer, that is to convert the input into stream of tokens. What else? If there is any space before this or after this line, that will also be removed by the lexical analyzer. Okay. Or if there is any comment, beside any line, then also that will be removed by the lexical analyzer. So what is the output of lexical analyzer? The output is a stream of tokens. Okay. So the responsibility of converting the stream of lexemes, A, B, C, etc. into stream of tokens. That is what the lexical analyzer does. Is it clear?
Lexemes means expression.
Lexeme means
Expressions.
I will tell you. Okay, lexeme means actually a meaningful sequence. Okay, meaningful sequence. And how to understand which one will be called a sequence? That when I will teach you lexical analysis in detail, maybe in the next class, I'll explain it with example, and that will be easy for you. Okay, so don't have to hurry or trouble yourself. Okay, so this is what we got as the output in the first state, that is lexical analysis. And this will go as input to the next state, which is the syntax analysis. So the syntax analyzer will take this as the input. Okay, so it takes token produced by the lexical analyzer as input and generates a parse tree or syntax tree. A parse tree is also called as syntax tree. Please note down this one. So don't get confused. Parse tree or syntax tree, both are the outputs of syntax analyzer. And what is this process called? This process is called syntax analysis as well as parsing. Sometimes it is also called parsing because you are producing a parse tree as the output, right? So syntax analyzer is going to take the tokens one by one and also a grammar, which is a context-free grammar. Now, what is a grammar? It has a set of rules. Okay. So whenever there is a programming language, it will always have a set of grammar. Suppose 100 lines or 150 lines rules or productions. Okay. Based on those rules or productions, the conversion will take place. Conversion means how the parse tree will be created, that will be taken care of using the context-free grammar and this productions, right? So what is basically grammar? The rules of entire programming language can be represented in few productions. You remember productions, right? This type of things, I think you have seen this type of writing in TOC. So if you have forgotten TOC, please brush up your concepts. Okay. So you see, generally every programming language will have few hundred of productions or rules. So based on these rules and taking the input, the parse tree will be created. Suppose this is a set of production. Okay. So what it is saying that, what is the meaning? A statement can be an identifier equal to expression. An expression can be expression plus term or a term. A term can be term into factor or factor. And a factor can be an identifier. So this is the set of rules that we have. Not all of them, but the one that we require as of now, we have taken those rules only. Okay. So we have the rules and we have the input, that is this one, the stream of tokens, and we are going to create a parse tree or a syntax tree using it. Okay. So let us see how this parse tree is constructed. So we will start with the first one, that is S. So what is S? It's a statement and it can be identifier equal to expression. So the statement can be identifier equal to expression. Okay, just see how this tree is created. Now next, expression can be expression plus term or term. Now which one you will use? There are two ways you can expand it. You can expand it as expression plus term or only term. Now which one to choose? Based on our input, you see there is a plus, right? So a plus must come in the parse tree. So since a plus is possible, so we will take this one. So expression equal to expression plus term. So expression is expression plus term, right? Next, if I see term, so term can be term into factor or factor. Now which one to take? Term into factor or only factor? So you see the input that we have. Here we have a multiplication in the second part. So we will take this one, term into factor, okay, and expand it the same way, term into factor, right? So other than that, we don't have any more operator. So now what we will do, now we will not take the productions with operators. Now we will take the productions without operators. That is, expression can be term, term can be factor, factor can be identifier. So expression can be term, term can be factor, factor can be identifier. Okay. Term can be factor, factor can be identifier. Factor can be identifier. Is it clear, whatever I said?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
If you don't understand, please let me know, because these are initial steps. If you don't understand this later on, you will face problem, because we have to, in every step, we have to create this type of trees. So now you see, I will draw it for you. So first is statement. So this is the tree that we have. So what you have to do is you have to traverse this tree top down, left to right. Okay, top down, left to right. So if I traverse it top down, left to right, what do I get? So we got the identifier. So identifier equal to, we'll take the last one. Okay? So identifier plus identifier into identifier. So we see that the parse tree that we have constructed, this matches with the input. So we can get this type of input from the grammar available to us. Okay, and since it matches, so we will say that this is correct. That means this is the syntax of this is correct. There is no syntax error in this piece of code. Did you get that? Did you get what I did? You just have to traverse, create the parse tree based on the grammar that is available to you. The grammar will be given to you. Okay. So based on the grammar, you have to construct the parse tree. Okay. And how you will construct the parse tree? Based on whatever input you have. If you can create a parse tree from where you can get this type of input, if you traverse it top down, left to right, then you can say that this is correct, but with syntax. Okay, that means there is no syntax error in this line. Did you get it?
Yes, ma'am.
Yes, ma'am.
So this process is called syntax analysis or parsing, because we are creating a parse tree. So this is called syntax analysis or parsing. Okay. And what is this? This is a syntax analyzer or parser. So now you got the tree. Okay. And you got the input also from this tree. So you can obtain this input from the tree. So this is correct. Syntax wise, this is correct. Now moving on to the next step. Okay. So this parse tree. Now we'll now go to the semantic analyzer. Okay. Now semantic analysis is a step where we have to, take care of few things. At this moment, it is difficult to make you understand that. Okay. So just know that as of now, just know that the parse tree will next, this parse tree will go to the semantic analyzer as input, and the parse tree obtained as output is semantically verified parse tree. Okay. If you get a semantically verified parse tree, then you can move to the next step. Okay. So the parse tree will be given to semantic analyzer, which will then verify it semantically. That is whether it is meaningful or not. Okay. Semantically verifying means whether this makes Now this one is, we have just seen that there are operators and there are these identifiers. So the way it is arranged is correct. But whether it is meaningful or not, whether it makes sense or not, that will be verified by the semantic analyzer. Okay, so this parse tree will be given as input to the semantic analyzer, and the semantic analyzer will verify its meaning, whether it is meaningful or not, whether this statement makes sense or not. Okay, if it after it is verified, then only it will move to the next step. Okay, how this verification is done, it's a bit complex process. So as of now, it is out of the scope to explain you with this example. Okay. But when we will study the steps, each and every step in detail, starting from lexical analysis, that time easily you will understand. So you don't have to worry. Okay. Okay, like what kind of meaning? So one example is given, like the left hand side has to be a variable. This one has to be a variable. If you want to store this value here, this has to be a variable. This cannot be a constant. Okay, so if it is saying that it is a constant and not a variable, that means this is incorrect. Okay, so though it is syntactically correct, but semantically it will become incorrect. So these things you have to verify in the semantic analysis phase. Okay. So the output of semantic analysis phase, that is the semantic analyzer, is also a parse tree, but that parse tree is semantically verified. That means it is meaningful. This line is meaningful. That is what it will say. So next step is intermediate code generator. Okay, so there are various ways of generating the intermediate code. I said that the most popular one is the tree address code. So the input to the intermediate code generator is a semantically verified parse tree, and the output generated is an intermediate code. In this case, it is a tree address code. Why it is called a tree address code? You see, in every line, there is maximum 3 address. 1, 2, 3. 1, 2, 3. Here we have 2, but I said maximum 3 address. Okay, so 2 is okay. In our initial input, how many addresses were there in the same line? 1, 2, 3, 4. Right? Now we will reduce it to 3 address code such that the meaning remains same, but there is maximum 3 address in each line. So we will take, for that we are going to take some temporary variables. In this case, T1, T2. So B into C, this multiplication will take place first, and the result is stored in a temporary variable T1, right? Now this T1 will be added with A, and the result is stored in a temporary variable T2. Then the result which is stored in the temporary variable will be moved to the final variable, that is X. Is it clear? Is it clear or not?
Yes, ma'am.
Okay. So up to this, whatever we have seen in the compiler, starting from the lexical analyzer up to intermediate code generator, up to this is the front end of compiler. Okay. And this part remains same for all the compilers. So if you want to create a new compiler for a different platform, you don't have to change these steps. You have to change the backend only. Okay. So the backend consists of the code optimization and the final one, that is final creation of assembly language. Okay. Okay. So now you see you have this 3 address code, and then we will see that, or the compiler will see that whether any optimization is possible. Okay. So you see this code will then go to code optimizer, and code optimizer will see that whether these 3 lines can be reduced to less number of lines. So you see T1 equal to B into C. Nothing can be done here. But in this one, you see T2 equal to A plus T1, and then T2 is transferred to X. So directly we can write X here instead of T2. X is equal to A plus T1. Still the meaning will remain same. There is no need of an extra temporary variable T2. So instead of T2, it will become X. Is it clear to you? So this is what we will get. Just see the difference. The meaning remains same. The meaning cannot be altered, but you just have to optimize the code. Is it clear to you?
Yes, ma'am.
Okay. Now this is the final optimized code. No further change is possible. This is the maximum optimization that was possible. So that is done. Okay. Now taking the intermediate code, the code optimizer is going to reduce the number of lines. So this is the number of, this is the lines that are reduced. Now next is the target code generator. This is going to generate the assembly code actually. So what it will do, it will take the variables, that is A, B, and C, and give it the registers. So suppose R0 is the register for A, R1 is the register for B, and R2 is the register for C. Okay. So what is the first step you see? Multiply B and C. So what is B? R1, and what is C? R2. So multiply R1, R2, and the result will be stored in R2. That is the second one. Okay, that is the meaning. So multiply R1, R2 and store the result in R2. Next, you have to add A plus T1. So what is T1? Basically, the result is stored in R2. And what is A? It is R0. So you have to add R0, that is A, with the result of the multiplication which is stored in R2. So R0, R2. Is it clear? Wait, if not, I'll tell you. Okay, so you have three variables A, B, and C. For this, you have taken the register names as R0, R1, and R2, right? Now the first step is, what was it? T1 is equal to B into C. So what is B and C? R1, R2. So we will multiply R1, R2. So what will happen? These two values will be multiplied and the final value will be stored in R2. Okay, that is the second one. Whichever register is present in second, in this case, the value will be stored here. Okay, so after multiplication, the final value is stored in R2. Next is X equal to A plus T1. So what is A? So add A is R0 and what? The final value of multiplication is stored in R2. So R2. Clear? Clear or not?
Yes, ma'am.
And finally, you have to move. Move what? Move R2 to X. Why? After addition, the value is stored in R2 now. So R2 has the final value of the entire, expression, and that value will be transferred to X. So this is your assembly code. Okay, an assembly code, as I said, is like a manual and it depends upon the platform. Like a manual is not applicable for different types of machines. Okay, it is machine dependent. So one manual will not work for another machine. Similarly, this assembly code is also like that. Okay. So in microprocessor, you will see that you write the code this way. This type of codes are written in microprocessor in that subject. So initially, programmers used to write code in this type of language, but then the language was modified and it was made more user friendly. And then came the high level language so that it becomes easier for the programmer to write the language. And this job was left on the compiler, that you convert it to assembly language, and from there, in the next step, in the consecutive steps, it will be converted to machine language. So this is a brief introduction about how compiler works. Okay, so some of the known compilers are GCC, okay, or you have Turbo C. These are some of the known compilers, and these compilers are a combination of all the things, starting from preprocessor to loader linker. That is why we get the final executable code and it is run in the machine to give the final output. Okay. So if I talk about only compiler, then the input to the compiler is the pure high level language and the output is assembly language. Okay. So I will share this PDF with you. You please go through the steps again. Whenever you get time, just revise. And if you are facing any problem or somewhere you could not understand, then just let me know in the next class. Okay.
Okay, ma'am.
So from the lexical analysis phase up to intermediate code generation phase, this is the front end. Okay. And the next two steps, that is optimization to target code generation, this is the back end. Okay. So whenever you have to make a compiler for another platform, you just have to change the back end. Front end work will remain the same. There is no need to change it because it is not machine dependent. Okay, this portion is machine dependent basically. So from optimization, we take it as the backend. Suppose you have a compiler that you are using in the laptop and you want to create a compiler for using in mobile. Okay, so that in that case, front end part, that is grammar, syntax analysis, semantic analysis, all those parts will remain same. What will change? The part which is machine dependent, that will change. That is the backend will change. Okay, other parts will remain the same. That is front end will remain the same for all the compilers. Okay, so I'll share it with you now. And I think you have a class tomorrow. So tomorrow we are going to discuss the phases of compiler starting from lexical analysis one by one in detail. Okay, so what is lexeme, how the tokens are generated from there, and everything we'll discuss. Okay, so next, after this, immediately in the next period, I have a class, so I have to stop it here. Okay. So if you have any problem, do let me know. And please go through this PDF. I'll share it right now. Go through this PDF and I will share whatever I will teach you. Based on that, I will also share other things, other stuffs, materials with you. Oh, Kyangshuman sir is already there. Sir, I'm done, sir. I'll just leave. Okay, thank you, students.